All right. So I'm Tim. I used to work at a startup called Predicto until we were recently acquired by United Technologies. So now I'm continuing as a software engineer there. I don't want to talk too much about myself, so let's get started. So, has anyone in the audience used Rust before or heard of Rust, I guess? Used it? Like maybe written a few lines of code? Okay. Anyone professionally? Yeah, I thought so. Yeah. Okay, so I guess first, I'll get into like a brief history of it. So like Rust started as a Mozilla employees side project in 2006. Um, Mozilla decided to sponsor the language in hopes they could use it to, improve Firefox. It went on to be used to build Servo, which was basically Servo was if you could rewrite the browser, if you could rewrite Firefox today, how would you do it, right? That was what Servo was supposed to be. So they rewrote most of like the browser engine in Servo. It's very experimental, and they wrote it in Rust. And the idea was they split it up into pretty isolated components. And the cool thing about the way they designed it is you can take parts of it out once they feel like it's ready for the prime time, and then they just put it into Firefox and you call over the FFI to Rust. So they decided to take they took the Stylo, the CSS engine, I believe, and maybe a few other components, and they moved it into Firefox from Servo. And that was the Firefox Quantum release, where they like doubled the performance of the browser. And so they were able to use Rust to like greatly improve the performance of Firefox. And they're continuing to like rewrite components here and there in Rust. So like I think MP4 demuxer and stuff like that, they've rewritten it in Rust, and they run it actually in the browser alongside the original C implementation, and they're actually verifying like, oh, that they 100% of the time produce the same output. But the nice thing about the having it in Rust is that it gives you a lot more like safety guarantees, and it just makes it a whole lot easier for people to maintain because you don't have to be a C expert, right? So Rust is a non-garbage collected systems level language. Its focus mainly is safety, performance, concurrency, and interoperability namely with C. So it's designed to make like systems level software more accessible for just the average developer, right? Um, the idea is you empower the developers to write low-level systems software by providing a language that's safe and doesn't allow you to shoot yourself in the foot, right? So I guess when is it appropriate to use Rust? So its main use cases are when you need like C-level performance without stumbling blocks of writing low-level code, or when you have applications where the cost of failure is very high, or where you need strong correctness and refactorability, because the compiler is very, very strict, and it keeps you from making a lot, like entire classes of mistakes at compile time. So another use case is like most of us today here in this room, probably write mostly like high-level languages, Python, Java, on top of some sort of virtual machine. And those allow us to write code very quickly, which is very nice because we can get prototypes like in Python, right? We can get prototypes out there very quickly and we can rapidly iterate. But a lot of times the problem becomes either safely refactoring that code or making it performant. So normally with like Python, you would have to drop into C if you wanted to write like a module in C to increase the performance. But the major problem with that is Python developers aren't generally going to be good C developers necessarily. You're not going to be a C expert. You're going to leak memory. You're going to segfault. You're going to make mistakes. Like I wouldn't trust myself to write a C extension for the Python code that I write at work, or probably any of my coworkers. But I feel like if we wrote some in Rust, I would have a much higher level of confidence in that code. So like some of the features it gives you is it won't segfault. It prevents entire classes of data races. It won't allow memory leaks at compile time. I mean, you can still have like object leaks where it's like, say you create a vector and you just loop infinitely putting data into the vector. You can still blow out your memory, but there's nothing that doesn't get freed in the C sense, I guess. And then the last feature it gives you is zero cost abstractions, which is just, people say it a lot and they don't really explain like what they mean by that, but it's basically just high level things like iterators and futures and things like that can, because the compiler is strict and can inspect lots of things about your code at compile time, it can tear down the abstractions. So like an iterator, and if you take an iterator and you map filter, and then collect, it can compile that down into a for loop, even though you wrote the functional code, right? Because it knows like, oh, you never mutated these things, or you never, it knows about immutability. It knows about how long things live and can optimize on that. So for example, like this is kind of a example of something you might write in C where you create a buffer of 4 characters, copy a string into it. Now you have a second pointer to this object. You free the first one by accident. This could happen like somewhere else in the code. You don't know, like maybe it got freed because you passed it into some function you didn't realize freed it. Then you try to print B. Now B is a pointer to bad memory. You've created a security vulnerability. You've created a bug. And then you free B, another security vulnerability. You double freed, right? And there's actually a third security vulnerability. I don't know if anyone can see it. Does anyone notice it? Stir copy.
Yes, stir copy, yeah.
You can't use stir. Stir copy is unsafe because if the string that you're copying into the buffer is too large, it doesn't check the bounds and will overflow the buffer. So this is just like an example of lots of like really, really common mistakes that can lead to security vulnerabilities, seg faults, all kinds of issues, right? So in like a simple Rust example, if you made a string like that, you have a reference to it. If foo gets moved or destroyed anywhere between the middle part and the print, that code won't compile because it doesn't allow you to create a reference that outlives an owned variable.
Now, is
So-
that let statement, just a quick question, that let statement immutable?
Yeah.
Or
Yeah, so there's 2 keywords. Let, it defaults to immutable. You can't change it. If you do let mute, it makes it mutable. But strings, I think, are always immutable. It's still a sane language. So the idea is that, so B is a reference to foo. If foo ever gets destroyed before this print happens, it won't compile because it detects that foo lives longer than B, which isn't a valid program, right? So there are a couple ways that pointers can be unsafe. So a lot of times unsafety comes into play when you have pointer aliasing and mutability. So aliasing just means you have multiple pointers to the same thing, right? And when you have lots of pointers to the same memory and all of them could be mutating it, you have lots of potential for bugs and mistakes. So Rust actually forces you to either alias or mutate, but not both. So at any given moment, you can have many immutable references to a memory region, or one mutable copy, or one mutable reference. You can't have both. It doesn't allow you to do that. Another thing is pointers never live longer than the data that they hold, so you can't have dangling references. Array types provide safe bounds checking, right? Unlike in languages like C, where it would just overflow the buffer and create a security vulnerability. It will panic, just blow up your program. And you can't create null. There's no null in the sense that other languages have null, like Java has null. You cannot create null pointers. So here's like an example of what Rust uses in place of null. So there's this type that's an enum called option. And it can either be some t, any type, or nothing. And basically it's a wrapper that you put around your object. And so that function get value, it can either return some string or none. And that is it. So whenever you call get value, so here we call get value equals, or foo equals get value, to even be able to access the string, we have to first check, is there something there? So is it nothing or is it something? So this is for those of you who aren't familiar with it, a match is kind of, pattern matching is kind of similar to, it's like an advanced switch almost, but it has a lot more like rich features, but you can think of it that way. It will force me to check every possible scenario. So if I didn't check whether or not it was none, if I left this line out, it wouldn't compile. It has to be exhaustive. So you have to check every variant. So in this way, Rust keeps me from making mistakes that you could make in other languages like Java, for example, where any place you could, like in Java, any place you can pass an object, you can also pass null, and then they do null dot function, null pointer exception. Your program blows up, right? In Rust, it forces you to check. It forces you to handle that case or explicitly blow up. So, and this kind of goes into like data races. So that same property that gives us some extra safety with references also can help us prevent data races, because since pointers must be exclusively aliased or mutated, it prevents many data races. Because if you think about it, data races normally happen when you have one pointer mutating something and then another pointer accessing it, right? So if you can't alias, but you can mutate, there's no data race, right? And if you have tons of aliases, but you can't mutate, no data race, right? But there are still times where things need to be shared between threads, maybe sent to another thread, or like shared simultaneously between multiple threads. And that's why Rust has the send and sync traits. And basically what those do is they're unsafe traits that, I'll explain what unsafe means in a minute, but they basically tell the compiler, send says, this type is safe to send to another thread. Sync says this type is safe to share with another thread, between multiple threads at the same time. So it means it's synchronized, right? So it will actually automatically implement sync or send where appropriate if it can detect that your type has certain properties that make it inherently send or sync. So for example, if your struct owns all of the data that it is in it, it is inherently send and will automatically implement the send trait, which is pretty nice. You can implement them manually for your type, but it's unsafe because the compiler can't guarantee that you have implemented synchronization properly, right? So you're basically telling the compiler, shut up, I know how to synchronize it, you know? Normally you won't implement these traits yourself. You will wrap your type in in an object that implements that trait. So there's an example is a mutex type in Rust implements sync. And it forces you to lock the mutex to get the reference to the object. So it can guarantee exclusivity when you mutate. And it gives it the sync trait. And that might be a little bit confusing, so if you guys have any questions.
For like cases where you're like doing like cache coherence, you know, like a distributed architecture, or even a multi-threaded scenario, and you're trying to have a cache where multiple have access to different resources, and you're using the sync trait. Does that mean that if an object gets dirtied, it'll automatically like update like all shared pointers to it? Like
No.
value or
Not necessarily. It just tells the compiler that when you send it to another thread, it doesn't have to move it.
okay.
Like it just says like this thing is safe to share between threads, and the compile won't fail when you try to.
Oh,
That's
okay.
all.
All right.
The implementation is left up to you.
Gotcha.
Normally though, you will just use some standard library type that implements sync and wrap your type in it, but you don't have to. So those are the standard library definitions of those traits. So they're unsafe auto traits, which means they will try to automatically implement it for your type if it can.
So those actually, they're empty traits?
They are, okay, yeah, they're empty. They're called marker traits, which means they don't have any methods you have to implement to implement that trait, but it just tells the compiler, you can use it as a generic bound. So you can say anything that is passed to me must be synchronized. and the compile will fail if it isn't. That's the whole point of marker traits. It tells you some inherent property of a type. Is really.
I'm a little more confused. How does the compiler know then to infer that something is a sync trait or?
You can do generic implementations for different types in Rust, and basically they just have code that just checks: does this struct own all of its traits? Does it own all of its fields? Does it own all these things? And if it does, it's automatically send.
Okay.
Or if all it contains is one mutex inside of it, maybe it's already sync, or something like that, basically. It tries to tell, but it can't always tell, and it'll just fail to compile when it can. And in which case, you will have to either implement sync or wrap it in a sync type.
You have to explicitly document it then.
Yes. So the way Rust guarantees no memory leaks is through the ownership system. And basically, there are 3 rules for the ownership system. Every value in Rust has a variable that's called its owner. There can only be one owner at a time, but you can pass ownership to someone else. But there can still only be one owner at a time. When the owner goes out of scope, the value will be dropped and deallocated. It's gone. Borrowing is like when you make a reference to something, so they call that a borrow. You can either do an immutable borrow or a mutable borrow. And if you make an immutable borrow, you can't also make a mutable one in the same context, because that would be aliasing and mutability at the same time. So any given time, you can only have either one of those things, right? And references must always be valid, which means that a borrow can't outlive the owned variable. This is probably a little confusing, so I'm going to go over some examples. So like the first example is pretty simple. So if you just create foo inside of a short scope defined right here. It is owned within that scope, and once the scope ends, it's automatically dropped and freed. So if you try to print it afterwards, fails to compile. Of course, if you've used languages that are like lexically scoped, this already would have failed anyways, but for the next one, this is kind of a better example. It's not obvious at first, but if you look at the function takeString, what this actually means, what the type signature means, is this function takes foo and it takes ownership of foo, because it's not a reference, so it must take ownership of it. So once this function completes, it actually drops foo and deallocates it. So inside this main function, you can see that we define the string bar and we store it in foo. And when we call this function, we have actually given ownership of foo to takeString. So once the function completes, foo is gone. I do not own it anymore. So then when I try to print it, this will fail to compile.
So that's not passed by value. It actually moves it.
It moves it onto the stack. Yeah.
So you're saying that not only does takeString no longer own it, but it's destroyed.
After the function completes, it's gone. Yeah, it gets deallocated.
So you cannot access it anymore after takeString function.
Exactly.
How do you copy strings then into a function? Can you do pass by value for strings at all in Rust?
Yeah, so you can pass references in, if that's what you mean. So for the next example, I show that with this, I've changed the signature of takeString a little bit to instead now it takes an immutable borrow of a string, so an immutable reference to a string. And now, once that function completes, it drops the borrow, but it never took ownership of the string, so it doesn't get dropped within that context. So instead, the function has to ask for a reference to that thing, an immutable reference to the thing. But if you don't put that it's a reference, it will take ownership.
No,
Instead.
What I meant, this is passed by reference, but like in C++, if you do not specify a reference, it will actually invoke the copy constructor and create a copy of the actual string. So you now have two
You have to
copies.
explicitly clone.
Okay, so you have to clone. Okay.
You have to explicitly clone. So I kind of like that too, because it actually forces you to write out that you're doing a copy. So there's no like you're never implicitly copying anything. So
it's always explicit copy.
yeah. So it's also more obvious the performance that your application is going to have. So with this example, I've changed it a little bit. So it takes an immutable borrow, drops the borrow after the function ends. Main has always maintained ownership of foo, and it will successfully print at the end and then drop foo at the end of main. So I never gave up ownership of it. I only gave immutable references to it out.
So
Anyone?
you can mutate the foo. Can you change the value in foo?
No, you can't mutate foo within take string. Yeah.
So you said earlier that every value has an owner, which is a variable. Is this just the variable you mean is the scope in which it's written?
Yeah. Yeah. So once that scope ends, if it was owned within that scope, it gets deallocated.
There's no particular name for that. It's just the scope that, I don't know, it's some symbol somewhere.
Yeah. No, it's just the scope that it's defined in.
What if you pass and mute string? Then can you mute the string?
I don't think so, because I think string doesn't really let you mutate the buffers inside of it, because strings are not supposed to be mutable.
If you had
But-
something like a car array.
Yes. If you had something like an array and you said ampersand mute and then the name foo, right? When you pass it in, you give it a mutable borrow to that function, and it could change it. But while that mutable borrow is happening, concurrently, you cannot have an immutable borrow at the same time, because that would be aliasing and mutability, right? So the rules seem a little tricky at first, but once you get used to it, it's actually very nice. And the compiler does a very good job of saying, like, it will have like arrows pointing to, hey, it was moved here, and you tried to access it here with like little pointers into your code, and it's very nice. So it makes it easy to kind of learn how the ownership system works. So the compiler feels like it's kind of working with you, you know.
You could also do data flow. You can actually see how the data is moving through your system.
Correct.
from abstractions.
And it forces you to think about your memory. Whereas in like garbage collected languages, you may not even think about how much memory your application's using, right? This kind of forces you to consider that.
When it drops, is it guaranteed to call drop at that point, or just drop at some point in time?
Yeah, it will call drop at that point. I'm pretty sure. It's not like with a garbage collector where you don't know when it might get
By
deleted.
default, Del, you don't know.
Yeah, you don't know.
If it will even happen. Right?
You don't know when or if it'll call
You're
Del.
like, you're like, please do this.
Please, yeah.
So when you're
Take
running,
this trash out.
when you're running certain things that might be algorithmic or wherever you have a lot of that going on, would there be times that you need to essentially coordinate when you're running those drops so that you're not hitting all of that at once
Yeah.
against the system?
Yeah, you might want to just,
Because a garbage collector optimizes for that intrinsically itself typically, right? Like
That's
when
correct.
to do the drops. In this case, I have to handle how to do the drop appropriately.
and I believe internally certain collections will actually use like memory arenas internally too. So it's not like you can optimize in unsafe ways. You can optimize code that has lots of like creates and drops, whereas a garbage collector would have been better, right? But you can still optimize for those things
Sleep
in Rust.
random.
What's that?
Sleep random, just at the end of the function.
Yeah, oh yeah, yeah. Problem solved. Yep. All right. So now I'm going to try to do some live coding for you guys. I like to live dangerously, so we'll see how it goes. If you guys have, if you want to, you can take your laptops out and install like Rust up or go to the Rust playground if you want to follow along, but you don't have to.
What is
So-
Rust up?
Rust up is like the Rust, like all-in-one kind of installer, package manager, and like
Oh, okay.
everything, right?
I brutally installed before coming here, so I didn't.
Yeah. So there's, if you actually look at my slides, this is the link. You can see the URL to my GitHub for this project right here. But yeah, or you could just Google Rust up. So anyways, let's get started. Wow, this is huge. So I have a few Python programs I've written here, and what I'm gonna do is rewrite these in Rust and kind of in the process show like the Rust way of doing the same thing, right? So here I've made a Python class called vector, and it has two fields, right? X and Y. It's a named tuple. When you add a vector with another vector, you add the components, which creates a new vector. It doesn't mutate the old ones, right? So when I make a vector here, and then I make a second vector, I print them out, and then I add them together and print them. So I'm going to rewrite this in Rust. Let me show the output first. So it's just vector 1, 2, vector 2, 3, vector 3, 5. So first, I guess I'll show you guys a little bit about the Rust package manager. So cargo is one of the best things about Rust, in my opinion. I think it was made by the Ruby guys. So they learned a lot of lessons from Ruby, and then they carried on those benefits to Rust. So when you start a new project, you just do Rust new, and I'm going to do Rust example 1. I have some solutions in case I can't figure it out. All right. So whenever you create a new project, by default, it has the cargo toml, which just defines all of the dependencies and information about the project itself.
We can talk about additions.
Additions, yeah. I mean, yeah. It's just basically the additions are just which like stable version of Rust you're on. So if you're on the edition 2018, it's the newest Rust, and it enables new language features that weren't available to older versions. That's all.
So if you specify the addition in your toml file, Rust will essentially figure out what version of Rust you're using, and then you can interact with older libraries.
Yeah, and then the cool thing is you can use the new language features, but still interact with libraries that are on older versions. Because a lot of times Rust will most of the time, and hopefully in the future, they maintain binary compatibility with the old Rust code, even though syntactical things have changed.
Is there a documented ABI for Rust?
I don't know about that. Yeah, I'm not sure. I know that it implements the C ABI. So that's most of the time how you end up calling to Rust from other languages. It implements the C ABI. And you can even generate C header files for Rust code. So you can call it to Rust from C. So bindgen. There's bindgen, there's C bindgen. Bindgen will generate C headers for Rust code. C bindgen generates Rust code for C headers. So
And WAS and bindgen.
yeah, WAS and bindgen is cool. So the default Rust file it makes, main.rs, just has hello world. So if you do cargo run, it'll compile it in the debug build and just print it out. So for me, that was kind of a big deal, having used things like Maven in the past, trying to get like a build set up and working correctly. It was never 2 lines of shell, so this was like incredible to me. So I made the Hello World project. So let me move over to IntelliJ. They actually have a pretty good Rust plugin for IntelliJ. I'm using that. All right. And it opens in the background for some reason. All right. Let me zoom that for you guys. Oh, wait, there it is. There we go. Not going to need any dependencies for this one. So let's take a look at the Python implementation. So in Python, we have a named tuple called vector with X and Y. So let's rewrite that in Rust. So we'll call it struct vector. X is a U32, and y is a u32. So in Rust, you don't have long int, long, all those like, you just specify it's this many bits, right? So there's u64, f32 for float, f64 for double. But let's, yes. Yeah, we could make this sign too. Doesn't really matter either way. Yeah. It's like magic for Java developers. Unsigned integers? All right. Here we go. So like Python, Rust has a trait called add. If you implement the add trait, you overload the add operator, and you can add, you can do simple plus symbol like that, and it is sugar for calling add, right?
So is operator overloading using all those underscore stuff same as Python?
No. So there's actually a trait, and like an interface that you can implement
Okay.
that will let it know you can add this with other things. So, and it's called add. I guess I can just open up the Rust add trait. So it just has a method one method called add. You define the output type, and yeah, that's it. You can also add it with a different type than the thing that you are using. So if you have a vector struct and you have a matrix struct, you can define addition between vectors and matrix, right? Which I guess probably doesn't make sense in real life, but just an example. So if I implement, first I have to import it. It's the standard ops add. All right. So now I'm going to implement the add trait for vector. All right. It's yelling at me because I haven't implemented the function. I do. I'll get to that one in a second. Actually, IntelliJ will.
Generate for you? Yeah, that's what I was wondering.
You can do that. It's pretty nice, actually. It outputs a vector. This is just an associated type. So in the trait, they wanted to define what the output of add was without specifying a concrete type. So they allow you to specify the concrete type by having this output type. So it outputs output. The right-hand side is a vector. All right. And so the implementation for this is pretty simple. You just create a vector with self dot x. Oh, yeah. My bad. Self dot x plus right-hand side dot x. And then y is self dot y plus right-hand side dot y. And that's it. Now you can add vectors together. So now if we go down to our main function, I can create a vector here. I guess I can't call it vec. I think that's a keyword. All right. Create a vector. And the example in the Python one was 1 and 2. I'll call this first. And then the second one was 2 and 3. And now I want to output the debug output of first plus second, right? So this is actually going to fail to compile, and I'll show you why. So it fails to compile because vector cannot be formatted with the debug format string because vector doesn't implement standard debug. So we got to implement debug for our vector. And this is actually one of the really nice things about Rust is that the standard library and lots of other libraries will actually generate code for you a lot of times. And you can just annotate your class as, or your struct, as deriving from debug, and it will generate the code to print this vector out as a debug string at compile time. So that code gets generated for us. Now if I run this again, I believe this will work, or it'll fail. Because main doesn't expect this, main doesn't expect to return a vector. It should be void. Basically, I forgot a semicolon. Because in Rust, whatever the last expression of a function is automatically the return value. So if you put a semicolon, it becomes a statement, and it doesn't return that value anymore. So let's try this again. And we print out 3.5. So that one was pretty simple example. But, oh, no, go ahead.
If you don't derive debug, you just implement debug.
I guess you could implement debug, but, I mean,
Right, in this case, you wouldn't, but.
yeah.
That's like a pretty, basically you can make it better pre-printer.
Yeah, it just allows you to format it as a debug string. It prints out all the fields, and it's kind of like a repr in Python, if you guys know about that. And there are lots of things you can derive from, which are pretty nice. Like if everything in your struct is implements copy, you can derive copy inherently, and basically certain built-in types implement copy, like integers. And what that means is when you pass it into a function, rather than transferring ownership, it just copies it because it's so small that it's just easy to just copy it onto the stack. And it does an implicit copy in that case.
Because the value is the same size as the pointer, basically.
Exactly. Sometimes smaller, right? Because it's 32-bit sometimes. So you can derive from things like that. And it's really nice because you don't have to write all the boilerplate code all the time or have IntelliJ generate it for you, right? But there is one small trick to what I just did that might be a problem. So you might have noticed that the signature of this function takes a vector, an owned vector. So that means that I consume the second vector when I create the new vector from the two added ones. So now if I try to print out the second one, which I have consumed, and I believe consumed the first one too, it will fail to compile because the value was moved here. And then it was used here after the move. So like I said, it's like you moved it here, and you used it here. Like it has pointers. It's really nice. It shows you everything you need to know to fix the problem. So this one is pretty simple to fix. All you have to do is, instead of implementing add for an owned vector, you can implement add for a borrowed vector. And it can output still an owned vector, and it still takes a borrowed vector. And then what we do is we get on here, and like the easiest way to do this is to just borrow it here, borrow it, and I believe
I think you just need to borrow the first, well.
it consumes both, I think, because self, to not consume self, you have to do reference to self, mutable reference to self. Yeah, because really, like it's not like an object in like Java or something where you have an implicit this. Self is literally just like when you call vector dot add another vector, it's really just sugar for add, pass in the first vector, pass in the second vector.
So it really implements uniform columns syntax, right?
Yeah, I don't know what that means, so.
Oh, so in C++, they actually added this, they're about to add this, hopefully, where you implement your functions like C functions, where the first argument is always the object.
Okay.
And
It's basically
then
that.
you could do object dot method name. And then
Yep.
So it's the same thing.
It's the same thing. Yep. So if I run this one, so it works now. So the first one generates a new vector based on references, mutable references to the first and second. And I know they won't be mutated because these are just immutable references. So Rust guarantees me that, right? And then I print out the second one. I can also print out the first one. Let's move it here so that it's just like the Python program. Run this guy. 1, 2, 2, 3, 3, 5. And if you take a look at our Python program, it's not much different, honestly. We have a whole lot less guarantees, but it's not less different. The output is pretty much the same.
Can you change the order in the Rust program for a second? So you change the order because you now made those references.
No, I just changed the order to be consistent with the Python program. Yeah, it doesn't matter in this case. So this is, I guess, a good example of like how you can write low-level code without having to worry too much about low-level details, right? Because this code is very, very similar to the high-level Python code. And we're able to write it in Rust and have it perform, and at the same time, still be pretty high-level and easy to use. So let's, I guess, move. Do we have any questions about this one, I guess?
Just a clarification on the earlier rules.
Sure.
You said that each value has a variable that is its owner.
Yes.
Doesn't look like there's a variable that
Ha
owns
ha ha.
vectors.
So when you define it statically like this, it's actually static in the binary of the application that gets generated. So it's
in this
owned.
case, it'll go into like the
Okay, so
data block.
yeah, so if you were to do this, okay, it's in the data block basically. Yes.
Or in the section.
So if you were to do it this way,
It's in the data section. So
so okay,
no,
Hold on.
no, the data section of the binary. So
yeah. So basically, what happens is if you define a literal
yeah.
in the binary, like in the source code, and then you immediately take a reference of it, it actually stores that literal in the application that gets shipped, and it lives for the lifetime of the app. So it's basically like a static in C or something like that. But in this case, I believe it will still probably optimize to do the same thing, but this is
It will, like in memory, it'll live like
Forever.
lists in C, but the Rust type checker says, this has been consumed.
yeah.
So I'm going to treat this memory as if it's blanked out now.
Yeah,
Okay.
yeah. That was a good catch. That was a good one. Yeah.
What if you derive copy?
If you derive copy, I don't think it probably doesn't make a huge difference.
And then it doesn't get consumed?
Yeah, it won't get consumed. Yeah, if you pass it in as like an owned struct, it won't get consumed if you implement copy. But generally, you don't really do that.
But
Right.
Copy is different from clone.
Copy is different from clone. Copy is implicit. Clone is explicit. So generally, you only use copy for types that are like the size of a pointer,
Yeah.
where the cost of copying it is the same as the cost of making a borrow, right? So you may as well just copy it onto the stack of the new function. Any other questions about this one? All right, let's move on to the next one. I don't know why it goes behind all these. I might run out of time, actually. All right. To change the interpreter. There we go. So this is an example of, I'll get more into like, I guess, functional, specifically functional programming in the Rust version for this one. So I define a person struct, right, in Python. I create a bunch of people with different ages. I find all the people that are over 30 with a list comprehension. I find how many are over 30, the sum of their ages, so I can find the average age, and then I print out the average. Pretty simple program. We run it and we print out the average. So I'm going to write this using functional, I guess, iterators in Rust. So let's go ahead, do the same thing here. Cargo, new, Rust ex2. change IntelliJ over. Oh, nope. SDX2. And it opens behind everything. Thanks, IntelliJ. All right. Okay. So the first thing I'm going to do is create the person struct. So, all right. We create a struct called person. They have an age, which is a unsigned integer. Can't have negative age. Create a list, static list of people. All right, let's kind of, maybe I can, let's try this. All right, let's just do this. All right.
Oh yeah, I think using vertical block.
All right. There we go. We have a list of people. All right. So I guess first, I guess we can kind of, oh, no, we can't cheat. So let's get the number of people over 30. 30. So we do people, and we get an iterator over, an immutable iterator over those people. If you wanted a mutable iterator, you have to do iter mute, right? So if we do a mutable iterator, we will filter all of the people whose age is greater than 30. I think I have to put that there. And then I'm going to count them. And I will have the number of people over 30. Then I will take, let's find the sum of the ages of people over 30. We filter the same way again. And then we just call sum. Oh, no, I'm sorry. Then we have to map, right, and extract the age out of the person. And then we sum the ages, and we will have that sum of all their ages. The problem with this is I expect that type inference in Rust is pretty nice, but it can't always perfectly predict what the type is going to be. I'm pretty sure that in this case I'm going to have to type hint this as U32, but I'll let it fail to compile so I can show you guys. Then I'll print out, let's see, the same string. Oh, that didn't work. Gotcha. All right, the average age of people over 30 is, and then we're going to put in, well, let's get the average. Average over 30 is the sum over 30 divided by num over 30. Right? Sorry, this is a little too long for you guys to see, but okay. So let's see. Let's try to run it. I think it'll fail to compile. There we go. Cannot infer type. Consider giving sum over 30 a type. So we have to hint to the compiler that the type of this is a U32.
Earlier it said it was a U size there.
Yeah, IntelliJ tries to figure it out.
Okay.
Can't always figure it out. Yeah.
U size is the size of the pointer.
Yeah, and it still thinks it's a U size. This should be a U32, right? Unless. Oh yeah, no, it does return a U size. That's correct. In that case, I just need to cast sum over 30 to a U size. Or, yeah, that's the safest way. Yeah, it tries to figure out what the types are and kind of adds them in visually for you. Yeah, it's kind of nice when it works. Still have a problem. We'll see. Expected U32. Oh, yeah. Data moved. Okay. Okay. That was an accident. Okay. So we calculate the average correctly now. And it prints it out. So now I'm going to show you guys how to parallelize this. And if you write code using iterators, especially like immutable iterators and things like that in Rust, it's actually very, very easy to parallelize. Yeah, what's up?
Go back to the Python one real quick. Wasn't the average the float there?
Oh yeah, because I used float division. That's right. I do need to cast these as an assigned int, don't I? Size.
So iSize gives you a float, or gives you a sign?
Not float.
No, that's a.
I'm sorry, guys.
Size.
F64. F64.
I size, I was like, wait a second.
Just kidding. There we go.
Honestly.
There we go. Just testing you guys. Okay. That's a good catch. So the nice thing about this is there's a Rust library called Rayon, and it makes it super, super easy to parallelize things like this where you're using iterators. I'll show you also, I guess, how easy it is to add a library to Rust project. I installed there's an extension for Cargo called Cargo Edit, and it makes it really easy to kind of like npm add a dependency. So you can do like cargo add. I think I installed it on this computer. We're about to find out. Rayon, and it goes into the toml. Oh, it's tiny, and it adds Rayon and finds the latest version for me. So that added the Rayon dependency. And so parallelizing this is actually pretty easy with Rayon. All you do is we import the Rayon prelude, which is familiar for Haskell programmers probably. It just brings all of the Rayon traits into scope for me. So now I can call pair iter, which is parallel iterator. And the same thing, it should still do the same thing, but Rayon actually behind the scenes, it will do things like work stealing and all kinds of awesome optimizations to make sure that it parallelizes it as fast as possible. So it kind of makes like a pipeline, sends all the data through each function you map over it as like a pipeline.
Does it do that? Does it just try to optimize that in parallel with like a single thread in which things are going through, or does it spin up multiple threads?
Multiple threads.
How does it determine how many it should use on a set of cores?
I think it defaults to like the number of cores, but I believe you can customize it. But I haven't had to do that yet. So we'll see if it works. Compiles a bunch of new dependencies. And there we go. That code now runs in parallel. So we wrote this code that was functional. It did immutable operations over our data set. And because of that, because of those functional guarantees, you can trivially parallelize this code. So it's very nice. Rayon is very cool. The guy that makes it super smart.
It's literally just the change from iter to hard iter.
Yep. It can do lots of very cool stuff. And so you can parallelize code very, very simply. Like, for example, I wrote an example project I did on my own was I was actually trying to implement the NNTP protocol for Usenet. You're probably familiar with that. And I was able to like create an app using Rayon that would pull down all the files and like stitch them together, and implemented Wine code to deserialize the data that I got. It was a really fun project. And then I just mapped all the functions I made, and then I changed it to pair iter, and you download all the parts in parallel, and it was just instantly parallelized it for me. So it's very nice. Any questions about this?
I was just wondering about, there's that tiny bit of duplication there. Is there a way to like, once it's filtered for everybody over 30, is there a way to like clone that?
You can collect.
Twice?
Yeah. You can collect into a vector, and then iterate over that vector instead.
Well, what if I wanted to just run through that iterator twice, if I'm using the right terminology?
Yeah, I know what you're saying. I'm honestly not sure. You might be able to. When I've had to do it in the past, I always just collected. And the Rust compiler is really good at like optimizing things like that, such that a lot of times.
Is there a dot
Doubling
reduce?
goes away.
What's that?
Is there a dot reduce?
Yeah.
I just call it reduce, and then you can do it yourself and return two things.
Yeah, probably.
But
There's
the fact that calling reduce on that filter is going to consume that filter stream.
That's what I think he would want to do, right?
Yeah, and then reduce, I would do
rather
mine to
return a
in the
operate.
sense of it would be used and not be usable again.
You're saying using a single loop to actually grab both the count and the sum at the same time?
No, I mean, I'm not really thinking about the performance as such as just like,
Yeah.
oh, why don't we make like in Python a generator of
Yeah.
everybody over 30 and then go through it twice.
Yeah.
Or
My-
one for just grabbing the count and one for mapping and summing.
My guess is that you probably can't. I think you would have to collect into a vector.
Even in Python with the generator,
Yeah.
you have stop iteration, right?
Yeah.
I mean, once it's done,
You can't go back over it again. Yeah.
Maybe it's just my Haskell coming back.
Yeah. I think Haskell can do that, right?
Immutable data structures generally.
Yeah. Yeah, I would be surprised. It might be able to, but I don't think so. Yeah, there are lots of functions provided on iterator. There's map, filter, for each, filter map.
And in the Haskell,
Reduce.
I think
Well, I mean,
it
in the
works the
Haskell
same
case,
way.
everything is lazy,
Right.
so
Yeah.
it'll generate it the whole
first
time, the
time.
first time, but
Right.
then it'll also lazily go over it and you won't have to collect.
Yeah. I'm not sure how well I'm doing on time here. Do I have time for another example, or
It's 8:03, so you have another about 10, 15 minutes.
10, 15 minutes? Well, I guess I'll try to go through the next example, and we'll see how it goes. But yeah, iterators are cool. It's where most of the functional code in Rust is. They have persistent data structures, immutable persistent data structures in this library called immutable, I think. It's very cool. They kind of implemented, kind of similar to Clojure. Clojure. They implemented those persistent data structures that internally do mutability, but provide an immutable interface to the user. So they do internal mutability for optimization. All right. So let's go to the third example. Man, I had so many slides. I didn't realize how quickly the time would go.
Very good discussion, so.
Yeah, I like it. All right. So just ignore, okay, I'll change the interpreter. Seven. So this is a simple example where I just read a CSVN in Python. I use the dictionary reader, so it comes in as like a map, basically. I extract the year, the row, the make, the model. It's like a list of cars. And then I print out the string. In year, make, built the model, model. It is a description, right? So I'm going to rewrite this in Rust using a library called Serde. It's one of the most incredible serialization libraries I've ever used. It's very, very cool. So basically what you do is you define these structs, and Serde will implement the deserializer and serializer for you using derives. So let me do this, ex3. So let me just go ahead and add Serde and Serde derive. Do I need anything else? I think that's it. And let's open this up. Maybe I should just skip straight to the solution since we're running short on time. Sorry, guys. There we go. So in my cargo tunnel, the only two dependencies are CSV and Serde, and then it offers a feature where it includes the derive traits with that library.
You specify those as two different packages, so they're not two different packages. Is this a specific?
You can do it either way. So you can have Serde include the derive crate, or you can actually specify them separately. Yeah. So this is the completed program. Let me zoom in. Sorry, guys. All right. So you just basically define a struct that, let me show you, I guess, the CSV too. So it's just the year, make, model, description, comma separated, standard CSV. So then you make some sort of struct, it doesn't matter what it is, and you just name the columns the same way, and you give it the types, and Serde will automatically try to deserialize into those types for you. And all you have to do is say derive deserialize, and Serde will generate all the deserialization code for you. You can also derive serialize, and it'll do the same thing. So our main function, all we do is we use the CSV reader to open in.csv. This returns a result, which I didn't get to yet, but it's similar to option in that, so with an option, it's either something with a value or nothing. A result is either okay with a value or error with an error type. And that's similar to Haskell where you have either, I think, something like that.
Yes.
Either. This returns a result, which means I have to handle the error case. In this case, I just panic. So I just chose, my program will panic with this error message. I expected in.csv in the working directory. But the really nice thing about this, compared to the Python program, is that in the Python one, there's not a lot of error handling, or it's not very clear where the errors might happen. You don't know what exceptions will be thrown. You don't know what the failure modes of your application are. Rust makes it very obvious because it returns a result. This thing can fail. You need to handle it, right? That file might not be there. When you deserialize, you get a result. That's either a record, which is my type defined up here, or a CSV error type. You have to handle the error case. It can fail to serialize. You don't want your application to necessarily exit at that point, or maybe you do. But the thing that I like is that Rust makes it obvious to me how my application can fail. So all we do is when you match on the deserialized object, I check if it's okay. I take the record out and I print it. And if there's a bad record, I print a failure message. But I don't stop executing. It keeps on going. Whereas the Python program, if it failed to deserialize, would have blown up and stopped executing. So I had the option here, right? And I know it, while I'm writing my code, how it can fail. So let's go ahead and run it.
So that into iter that generates the iterator object for you?
So into iter is another kind of iter. iterator. So there's iter, itermute, into iter. Iter is an immutable iterator. Itermute, you get a mutable reference. And then into iter, you get an owned copy. So it's just moving it. So there you go, it compiled, and it prints out those 2 lines successfully. But I would like to point out that if I were to add a new line, and this, let's say I copied this last one, and I say foo. So this is no longer a valid integer. And year has to be an unsigned 16-bit integer. So when I run it, it will fail, but it will continue executing, but it'll print out this error message where it hit this match and went through the error branch and printed out, hey, on line 4, byte 108, there's an invalid digit in the string.
Would it stop there, or would it just keep continuing?
As this is written, it would continue, unless I, if I did something here, like if I made this a panic and say it like, oh, I want the program to exit. But if I don't want it to exit, I can just print out an error message, let them know what happened, keep on going. Right? So I can potentially handle these errors properly. And usually error types are going to be some sort of enum. So you can also be like, oh, if it's this kind of error or this kind of error, if it's an IO error that is of type read timeout, retry. But if it's a different kind of error, blow up. Right? So you can handle different types of errors very easily using match statements and stuff. Any questions about this example? I guess that's it. Thanks, guys.